A very good afternoon to one and all present in this virtual platform. At the very outset, on behalf of School of Civil Engineering, KIT University, I, Dr. Madhulisa Patnaik, coordinator of this FDP program, conveys a warm welcome to our guest, Dr. Arindam Dai, in this online 5-day faculty development program on recent advances in forensic analysis in civil engineering, which is sponsored by AICT Training and Learning ATAL Academy during 27 September to 1st October 2021. So today is our third day. So now we are going to start our session 9 on forensic analysis of hill slope instability by Dr. Arindam Dai. Now I would like to take privilege to introduce our guest. Dr. Arindam Dai is currently an associate professor in the Geotechnical Engineering Division, Department of Civil Engineering, Indian Institute of Technology, Guwahati. He obtained his B from Javadpur University, Kolkata in 2003, followed by MTech in 2005 and PhD in 2009 from IIT Kanpur. Before joining to IIT Guwahati in 2011, he has been postdoctoral fellow at University of Molise, Italy. He works in varied field of geotechnical engineering, including foundation engineering, geotechnical earthquake engineering, geophysical investigation, computational geotechniques, slope stability, and landslides, soil structures, interaction, and forensic geotechnical engineering. His current research group includes 10 PhD students and 3 MTech students and has already supervised 8 PhDs and 22 MTech students. His research group has more than 250 technical contributions in international national journals and conference seminar proceedings, including books, chapter, and technical reports. He is a member of several professional bodies, including ISS MGE TC2080 Committee on Slope Stability and Landslides, IGC, TRG, and IEI, and FOSCT. And he has received several research awards and has been an active research consultant in the area of geotechnical engineering. He has been involved with several prestigious sponsored research, DST, NRDMS, and JSPS, and consultancy projects from several clients like NFR, NHI, PWD, CPWD, Saproji, and Palonji, RIDE, Simplex, Infrastructure, and many more. So not taking much time, I would like to invite Dr. Arindam Dai to please start the session. Over to you, sir.
Okay, thank you so much, Dr. Madhulisa, for the introduction. So without wasting more time, let us move ahead to the presentation. I'm starting to share my screen. So I hope you are able to see my screen.
Yes, sir, it is visible. Fine.
Okay. So good afternoon, one and all, to all the participants who are present here. So in this particular talk, we will be having a discussion about the forensic analysis about a hill slope instability, where we had worked upon a particular project where we were called upon to examine why a hill slope had failed, and upon finding the reasons, whether we could do something about that. So in this particular topic, one of the most interesting word is forensic, over which this particular FDP program is based. So I think based on the previous lectures, now you are quite aware what is basically a forensic analysis, what we do here. So in the forensic analysis, we mainly target to find out the background or the hidden reason why a specific event have occurred. Now, when we talk about slope instabilities, different types of slope failures take place. Slope comprises of different type of material, be it the fine soil, be it a gravelly type of material, be it a rock conglomerate soil mixture type of material, and such various types of slopes fail under various causes. And these causes extend from the natural ones like rainfall, seismicity, or from thousands of anthropogenic or other morphological changes. Some pictures, what you see here are various representations of slope failures. The first one is from Arunachal Pradesh, Pandetdewa, where a mudslide has taken place due to extreme rainfall. From Saipo, Mizoram, you can see this picture, which has where the slope failure took place due to seismic action and faulty construction technique. Similarly, in some location in Guwahati, Assam. Sometimes rock fall do occur near Gurafam, near IIT Mandi. Sometimes out of nothing, due to some natural cause, due to some accumulation of water, huge landslides take place, which you can see in Shonapur, Assam, or behind the Tawang Monastery in Arunachal Pradesh. So all around, we have such type of failures. And as I was mentioning, the causes are plenty, including the geological causes, the morphological causes, the hydrological causes. And all these different types of causes, including the anthropogenic ones, where the human interferences take place. So all these different types of causes lead a stable slope to a marginally stable one. Marginally stable means where the slope is on the verge of the failure. So it has not yet failed. And then due to some triggering effects, such as it might be rainfall, it might be a seismic action which has taken place nearby, or even due to some toe excavation of the hill slopes for extending the roadways or the railways or even the inhabitation. So such triggers lead to the failure of the slope. Now, in most of the cases, when we, as a geotechnical engineer, when we look into these type of events, so mostly we are basically called in cases where the event has already taken place. And then we are asked that what all mitigation measures can we possibly adapt to prevent such happenings in future. Now, there are thousands of mitigation measures. Each different mitigation measures call for different type of understanding of the failure. And that's where the forensic word comes into picture. So you go to a site, see a failure, try to find out its root cause, and then go for the next step of mitigation or restoration or whatever you want to do with that project. So I was looking through the schedule and I saw Professor Babu had a presentation on forensic geotechnology, its issues. So I am pretty sure that Professor Babu has given a glimpse about what is forensic geotechnology, just maybe for our recap and for the sake of this presentation over which we will use these terms. So whenever we look into forensic geotechnology, we have a framework over which we try to do some of this analysis. And this starts not only from, it does not start directly from the analysis, but in the very first step, we sit down the table, we make a discussion before even making a reconnaissance survey. So most of the times the clients will come to you about telling about the project, what damages they have incurred. And that is what is a pre-reconnaissance roundtable discussion. Then based on this pre-reconnaissance roundtable discussion, when we get a know-how of the project, then we really need to go to the site. We make a reconnaissance survey at the site where we really collect the evidences. We inspect the site, what has happened, and try to figure out what has really occurred over the period of time. We talk to different eyewitnesses. We talk to the people who have suffered due to the calamity. We collect specimens from the site. So soil specimen, rock specimen, or any other visual inference which we can draw from visiting the site. And if and at all there are measurement or monitoring data, if the agent or if the client has already done some monitoring, we definitely need to collect those as well. Now from this reconnaissance survey, by talking to the eyewitness and everybody, we try to decipher the chronological event, how the event has taken place over the time. One thing we should understand that none of the failures are all very sudden. Every failure gives you certain indication over the time, and how that has taken place over the time is very important to know. And not only that, many times, as I was mentioning, that there might be some rainfall event, some seismic event, some inhabitation, some infrastructure construction has taken place, how they have been done over the time, and whether they have any relationship with the failure over the or the evolution of the failure. So those we try to decipher from these chronological events. And based on all this idea, from whatever we find in reconnaissance, whatever understanding we develop based on the events chronologically which took place, we try to develop a preliminary model. Now, preliminary in the sense that definitely when you do a forensic analysis, all the information will not be available to you. Some of the information will be hidden. Over the time, we may carry out some more experiment. But at the beginning, we start developing a model preliminarily with whatever data and information you have. And once you develop the model, you carry out a failure analysis. And as mentioned, these preliminary models will have many assumptions, many unknown assumptions, which may or may not fit into the problem, but you have to figure it out over the duration of the analysis itself. And the main target is to basically figure out what was the cause, effect, and the triggers which has resulted in the failure. Now, the next important step in this framework basically comprises updating the model, because as I was mentioning, the preliminary model will have several assumptions. And over the time, you need to figure out during the flow of the analysis, you need to figure out what is missing. And if necessary, you need to carry out some more experimental investigation, whether it is directly in the field or whether you bring some more samples in the lab and experiment them out. And based on the new information, you update your preliminary model and see how things are matching with each other. And at the end of the forensic investigation, if the scope of the project really requires the development of some remedial measures, so that also forms an associative part of the project. Now, one thing which we should always remember in forensic geotechnology is that apart from the technical data, which you collect from the measurement and monitoring sites, or from the laboratory and field investigations, a big role is played by the visual information which you collect from the site during the reconnaissance, during the inspection of the site, during talking with the eyewitness. And once you visit the site, many information you will be getting which are not readily quantifiable. So there are qualitative information, but from your preliminary models or the updated models, we need to set up a validation with those observational data as well. So forensic geotechnology comprises a section of geotechnical investigation, where the technical data, the measurable or the quantifiable data goes hand in hand with the qualitative evidences, whatever we collect from the site. So based on this framework, let us, I will show you a case study where in Umrangsu in Assam, behind a cement plant, a big landslide had occurred, and we were called upon to find out the cause of this landslide, why did it happen, and then we figure out if we can adopt certain remedial measures to prevent such things happening in the same site in future. So whatever picture you are seeing here, so this is the part, whatever you are seeing in the front has actually been affected by the landslide. From the screen towards the far end of the screen, everything has slid down. So these are the retaining walls. So this is a panoramic view. The retaining wall goes like this, and due to the movement of the soil, this retaining wall actually has got disturbed and snapped at several places. On the left-hand side of the retaining wall, on the field side, you can see some building. So those are the workshop and the storehouse buildings which were there for the cement plant. So the Umrangsu is a small inhabitation area located at the Assam-Meghalaya border. And a few important information which we should know for this place is, most importantly, that it has a very high average annual rainfall. So this rainfall also serves as a point of trigger in the sense that heavy runoff takes place, surface runoff takes place. Apart from that, a lot of percolation of water also takes place in the shallower level, and which triggers landslides a lot in this entire area. So we are talking about this particular cement factory, and based upon some of the anthropogenic construction activities and some natural interventions. So there has been a landslide on the left-hand side, and you can see the direction of the landslide moving away from the factory building towards the valley side. At the bottom, there is a small nala which is flowing, carrying water. And in such incidences, it is always expected that there will be some seeping taking place from the top of the hill or the crest of the hill where the factory is there towards the nala or towards the downhill side. So as mentioned earlier, that we have some framework over which we do a forensic study. So we started with a pre-reconnaissance roundtable discussion. On 2nd November 2015, we met with the client where we were presented with several pictures about the damages of the residential housing block 24 colony. So this is a residential colony set up for the cement factory workers on the sloping face of the hill over which the landslide has taken place. So 2 rows of 12 quarters each were located there at that sloping face, and all were extensively damaged. So we could see from their pictures the crackings in the wall and the floor, and the width of the cracks were so high that we basically can see from one side to the other. So we could basically name them as the see-through cracks. There were detachment of plasters. The stud columns or stud slabs also got cracked. And what was noticed from the records of the workers who stayed there for quite some days, that during the night, abnormal sounds used to come, which was basically due to cracking, snapping sounds, creaking sounds used to come. So those were being conveyed to us. The photograph shows that there is heavy detachment in the floor. So the walls and the floor slabs got detached. And even to the extent that the soil near the plinth raft got shifted. So you can see that the soil has moved away and the bottom portion of the plinth got exposed. And over and above that, in that entire area, there were several retaining and boundary walls, which also got damaged. Now, just to mention that these retaining walls were heavy boulder rubble masonry retaining wall, which have enormous strength and they're not very easily damaged. But it happened in this particular location that every one of them got damaged, and from that we could make an idea how much of stress lateral thrust would have come on the retaining wall due to the movement. So enough amount of deformation would have taken place. So there has been development of gaps and cracks in the retaining walls. 4 different retaining walls were there between the storehouse and the workers' colony on the downhill side. So retaining wall 1 was the highest one, the most robust or rugged retaining wall, which also showed several locations of cracking and snapping out. Retaining wall 3 was just beside or just downhill the retaining wall, which was constructed to protect a road when it was seen that the access road was getting damaged due to the movement. And you can see the cracks in the retaining wall 3 as well. And you can see that the crack is not only wide, but the retaining wall has shifted from its position and snapped away from each other. The retaining wall 2 is basically just in front of the workers' colony that was constructed to protect the workers' colony from the initial movement and expected damage. But this retaining wall 2 over the time also suffered heavy damage. You can see wide cracks, and there has been a lot of toppling of the retaining wall as well. And there was some old boundary wall all around the colony, and that got heavily snapped and detached. And along with that, when the soil started to move from the uphill location to the downhill colony, in the workers' colony, there has been severe dislodgement of the pavements. The drains got blocked because of the movement of the mass of soil. And we then looked into what the contour map wanted to show us. So the contour map showed that there is basically a gentler slope at the beginning, and then there is a steep slope, and this location is basically the workers' colony. So these on the left-hand side of the polygonal demarcation, these are the storehouse and the workshop, and the slide took place in the direction of the arrow, moving or in this process damaging the workers' colony. So what we did in that pre-reconnaissance roundtable discussion, apart from seeing these pictures, we tried to make some idea that what is the elevation, what are the things constructed, and which is a very important thing to be done in forensic geotechnical engineering. Before moving into all the sophisticated technologies, you should sit down with the pen and paper, discuss with the client, and then figure out what happened. So this is basically elevation view of that particular section. So this is the plant housing the workshop, storehouse, everything. And you can see that there is a gentler slope at the beginning, and then there is a very steep slope. So from this discussion, we also tried to figure out where and which place or how much distance the damaged areas are located. So we could figure out that this is the storehouse, which is quite some distance from the plant, mostly on the crest of the slope. And beyond the storehouse, the dip of the slope face started taking place. So after the storehouse was constructed, so people noticed that there has been a small movement because of certain amount of rainfall which took place in the year 2014, and they immediately constructed the retaining wall 1. But beyond that retaining wall, even after that construction, again over the year 2015, when further rainfall took place at the beginning of the monsoon season, they could see that the workers' colony were slowly getting damaged, and they created the retaining wall RW3. Now, it was believed that construction of this retaining wall would protect the 24 housing colony, but it didn't happen. Not only that, because of the movement in the downhill direction, one access road which passed in front between retaining wall 1 and 3, that was starting to move. Now, if that access road is blocked, then the roadway to the cement plant, to the southern side of the cement plant would have been disrupted. So RW2 was constructed to protect the movement of the road. But unfortunately, nothing happened. So everything started moving, and on one fine day, after quite some showers of rainfall, the entire slope collapsed. There was another retaining wall 4, which was constructed in between, thinking that this retaining wall 4 would protect the slope, but it was quite downhill and it did not serve any purpose. We'll see later. So if we see the plan view, so this is the workshop and the storehouse building. We have the retaining wall 1 in front of that, the biggest one. Then this is the 24 colony. We have the retaining wall 3 in front of that. So we have retaining wall 2 in between with access road going between them, and retaining wall 4 is at the lowermost point, which is not shown here. So we decided that without wasting any time, we should go to the next phase of the forensic study. That is, we should make a reconnaissance site visit. So we went to the site, and we saw several demarcations of extreme movement, and we could figure out small hints about what could have happened. We could see, so whatever building you are seeing here on this top left figure, this is the workshop storehouse building. So we could see that from below the building itself, the soil has moved out from the plinth level. That means this building definitely have played some part in triggering the movement, and probably the extreme rain which had taken place over the time. So that had led to further erosion of the soil and dislodgement of the soil covers for the embedment of the footing. The movement of the soil exposed the underground constructions, the utility lines got damaged, and this is the retaining wall 1, which is just in front of the workshop building to prevent any movement. So that retaining wall was constructed with quite a big height, quite a big thickness. Base thickness was quite high. But even all after doing that, you can see that a huge snap of the retaining wall 1 has taken place in this location. So not only at one location, 3-4 locations have really snapped out. Then we moved downhill from retaining wall 1 towards downhill. We could see that in this location, the condition was very muddy. That means the water is accumulating there. So this is indicating a good amount of seepage occurring from the uphill part. Most of the drainages were choked due to the mud flowing into. And further downhill, we could see large longitudinal cracks. So all these thick cracks propagating longitudinally could be seen one after the other, which basically indicates mass movement of the soil in the orthogonal direction, from the left to the right. Then looking further below from this point, we could see the beginning of the 24 colony, and you can see huge amount of soil accumulation. And these soil basically are the ones which moved from the upper region, and they got accumulated here. One small retaining wall was there, RW2, but this RW2 also, you can see the condition that this retaining wall snapped to a very large extent. So after the retaining wall snaps, it topples and there is no further purpose which it can serve. Then we moved on to the workers' colony itself. We could see that the closest retaining wall to the workers' colony, or a breast wall, that also was basically moving towards the workers' colony. The wall is getting pushed by the huge amount of soil thrust coming from the uphill side. And due to that, you can see that there are breakages of the drains and the drain covers due to pressures from both the sides. Then we moved further downhill, and when we moved to the other side of the 24 housing colony, we could see large size longitudinal tension crack, lot of separation of the soil from the building foundations, and damages in the floor slab, RCC construction, everything could be noticed. And then we came to the final spot. This is the location where the slope is extremely steep. So we are looking it from another hill on the other side. And we are seeing this slope to be extremely steep. And this entire area got slid, taking the workers' colony with it and doing extensive damage to the entire downhill section. And you can see that there has been overflow of the mud. So muddy water or muddy soil water mixture has flown over this area. So here there was a nala which got completely choked because of this mud flow. And then that also basically triggered probably more response of landslide into the area. Some pictures from the colony, you can see that it is an extensive damage. Now, this picture on the left-hand side is very interesting because looking at this, we could get some inference from the field. So this is the immense amount of mass movement and the direction which occurred in the downhill of the slope just behind the workers' colony, and the entire workers' colony got damaged due to that movement. You could see that broken boundary wall, which I was showing in one of the previous slides. So you can see that the wall has been snapped off. A portion of the wall actually crumbled down with the moving soil mass. Many places we could see seepage water was ejecting out, not only as a muddy flow, but sometimes small springs water is gushing out as well. Then we could see the retaining wall RW4, which was constructed at the very bottom, thinking of serving some protection, but it did not serve anything because the much above that the soil mass failed and it actually overtopped the retaining wall, and some portions of the retaining wall was basically washed away with the moving soil mass. So then the next phase we look into, where we try to collect some information and data from the site. We asked the client that what all the information, geotechnical information you have at the site. So this is the cement plant. So this is the area where the landslide has taken place, and this is the southern section of the cement plant. But then what we could know from the client that at the location of the landslide, since they were only constructing some workers' colony with the access road for the southern part, so they really did not do any geotechnical investigation here, thinking that the workers' colony are only lightweight structures and it is not supposed to do extensive damage. So we could figure out that over the plant area, there were some geotechnical investigations done. Borehole stratigraphy was there, some dynamic load tests were there, some cyclic plate load tests were there, CBR, California bearing ratio test, trial pits, all those were done in the plant area. So what we did not have is the actual information of the sloping face of the hill. So still, as I was mentioning earlier, in any forensic investigation, you would not get a complete information right at the beginning. So you have to start with whatever you have at hand. So what we could see is that based on whatever boreholes they had all around the plant area, so our study area, that is the downhill area where the landslide has taken place, we could figure out that 3 boreholes were very nearby to that. So we took those 3 boreholes into our consideration and started working on the preliminary assessment. But again, to remember, over this study area, we did not have any borehole, and these boreholes were mostly on the crest of the hill. So it may concur or it may not concur with the sloping face of the hill, because sloping faces many times provide a different types of geology and geomorphology. Nevertheless, we took those 3 boreholes into consideration. And what we tried to understand from these boreholes, how the soil profiles were changing over that in area covered by the 3 borehole. And then we tried to make an assertion that, okay, we will carry out some analysis considering each of the borehole. And from each of the borehole, we will consider some soil stratigraphy. And then we will do some preliminary analysis to see how similar or how dissimilar we are from the field observations. Then we had some more advantage in that area, the movement having been taken place from the year 2014, what the clients, the cement cement factory management agency have done, they had put many displacement monitoring stations all around this hill. So they have put some displacement monitoring stations right at the workshop and the storehouse, at the retaining walls, various retaining walls, around the workers' colony, and even near the downhill on the southern side of the on the eastern side of the workers' colony. So based on this displacement monitoring station, some records had been taken till 2015, but till November or December 2015. But you can see that some of these monitoring stations are written as point destroyed. So this movement took place to such an extent that some of the retaining walls toppled. Some of the soil mass movement was so high that the monitoring points were destroyed and no records could be further taken. And these records, whatever we had, gave us not only the lateral displacement which took place, but some vertical displacement as well. Now, since many of those points were destroyed over the first 19 locations of monitoring points, the agency had put some more points from March 2016, 17 new locations were figured out, and then a new set of monitoring stations were adopted for that site. So we had some records or some idea about how much of displacement took place over this entire cross-section area. And that would help us when we develop the preliminary model and give a certain idea how similar or dissimilar the things are. So this is the contour plan of that area. So from this contour plan and with further discussion, we tried to figure out that what is the chronological event that took place. So the storehouse and workshop was constructed first, and this workshop and this 24 housing colony area was also constructed over the due time. People noticed that there is movement of the soil mass downhill from the storehouse. Now, to prevent any further movement or damage in the downhill side, this big retaining wall R1 was constructed, covering all the entire width of these structures. However, it was noticed that it was still moving, the soil was still moving. So the next important area was the colony area that should not get dismantled due to the movement of soil mass. So this retaining wall R2 was constructed. Still in between R1 and R2, the movement was being seen, and this access road was getting dislodged. So a retaining wall R3 on the eastern side of the access road was further constructed. And finally, still when movement was still noticed, in between at certain time, a small buttress retaining wall at the toe of the slope was constructed to prevent, with an idea that the toe of the hill slope shouldn't move, and probably that would save further movement. So that was the sequence of events: storehouse, workshop first, then R1, then R2 in front of the colony area, R3 was constructed, and finally R4. So what we did is that all along this contour area, we took some cross sections. So you can see one big cross section going from storehouse to R4. So we have 3 cross sections taken all along so that we can figure out what is the topography of the hill slope, what are the slope dimensions, what is the extent of the hill slope over which we have to define our preliminary model. So this extent, this lateral extent over the cross section AB, that is the longest one, is around 240 meters, and the hill slope was around 17 to 21 meters high. And then we could locate at which place each of these constructions has been made. So with this information, we started to work upon the preliminary model. We used the software GeoStudio to set up the model and do some preliminary failure analysis. Now, 2 challenges came in front of us, as there were no boreholes at the particular location of the landslide site. So we did this soil layering on the basis of the nearby borehole stratigraphies. Remember that I mentioned we took 3 boreholes. So we made 3 different models: primary, secondary, and tertiary model. For each of the model, we took the stratigraphy from each of the borehole. And then based on the sloping nature of the hill, we could trace out some assumptive soil layering. And from the boreholes, from the geotechnical investigation report, for each of these soil layer, the shear strength and stiffness and other parameters were provided. We took that into consideration. Other factor which was unknown to us, what is the depth of the water table. Since we do not have any borehole on the landslide site, the water table could not be located. So in that case, what we assumed is that we will do trial and error executions of the preliminary model with different levels of water table. So one water table, W1, we considered as very shallow. W2, we considered for a next set of analysis at the interface of soil layer 1 and 2. And again, for a third set of analysis, between soil layer 2 and 3, we considered the water table layer W3. Now, these are the natural water table or the seepage phreatic line which we considered for the analysis, assumptive. We really do not know where the water table is. But then our target of doing this was that if we can figure out the water table and we can see that whether the sliding is taking place accordingly, what has happened in the field, then we could get some idea from that. So that means we have 3 models of 3 different soil layering, and for each of the model we have executed them under dry condition and 3 conditions of water table. So total 12 runs we made, but there were several trial and error with different types of stratifications. All those were done. So the material properties as mentioned for each of the soil layer models. So PM is the primary model taken from the first borehole. SM is the secondary model taken from the second borehole. And TM is the third or the tertiary model taken from the third borehole. So all the parameters which were obtained from the geotechnical investigation report already done at the site. So those parameters we used to set up the soil structure model over that particular landslide area for the numerical simulation. We also wanted to model the retaining walls as they were, not simply like a barrier, but as the way they were constructed at the site. So from the site investigation itself, we took some lump sum measurements for the retaining wall R1, R2, R3, and R4. And these are some of the sections. You can see that the R1 retaining wall is quite bulky. R2 and R4 are very short height and only to protect some local dislodgements. And R3, which was just beside the access road, was just used as a temporary measure to stop any movement of the road. So we took these sections of the retaining wall, and when we modeled in GeoStudio, we modeled in exactly the same manner they were. Now, if you remember that I was talking about deciphering the chronological event, and one of the main importance of doing that is that when you do the modeling, you should follow the same sequence of event, and then only you will be probably in a position to figure out how the landslide had taken place. So we cannot basically put all the retaining walls together, and we cannot put all the building loads together and see whether it is triggering the landslide or not. It might trigger, but still the chronology of the triggering event will not be clear to us. So when we started looking into the preliminary models and carry out their failure analysis, so we started modeling them sequentially. We started to look into the sequential anthropogenic intervention, various types of constructions, which has been taken place in the site. But at the very beginning, you need to ensure that what is the stability of the virgin slope before any human intervention, before any infrastructure construction, from the in situ analysis. So from the in situ analysis, so that was our stage 1 of any of the analysis, that we carry out an in situ analysis to see whether the slope was safe or stable before the human intervention. Because in the site, we came to know that before the construction of this plant or the storehouse, the slope was absolutely stable, and that needs to be verified as well. Stage 2 is the excavation of the foundation of the building, that workshop and storehouse. So we could remove the soil from here based on the foundation details which we have obtained from the site. Now, after you remove or excavate this soil mass, so you will construct the building. So that means building load will be imposed. So stage 3 is the case where the building load is imposed. And after you have constructed the foundation, so you need to backfill the soil mass there. You cannot leave the foundation open. So stage 4 is the case where the backfilling of the soil mass in the excavated soil area was done. Now in the actual site, stage 3 and stage 4 will be done simultaneously. Here we had done a little bit separately. That doesn't change the scenario too much. Stage 5 So if you remember the chronological event, that after the construction of the building, the things started moving. So they constructed retaining wall 1. Now the retaining wall 1 was a big one. So they need to again excavate for its foundation. So stage 5 is the stage where the foundation of retaining wall R1 is excavated. And stage 6 is the construction of the retaining wall following with the backfill. So this backfill, now again, there was one issue is that generally we use a properly good drainage material as the backfill, mostly sandy type of material where it can be free draining. But in this site, nothing was done alike. So whatever local soil material was available, that was dumped and compacted, and that served as the backfill. And who knows, that also accumulated the water and gave extra thrust on the retaining wall, leading to its movement. So stage 6 construction of R1 is completed. Now, if you remember that after the construction of R1, on the steeper face of the slope, we had the housing colony. To protect that housing colony, R2 was constructed. So excavation for R2 was done at stage 7, and stage 8, R2 was completely constructed. After this, still movement was seen in the intermediate portion where the access road was passing through. And so the retaining wall R3 was constructed. So stage 9 is the excavation for foundation of R3, and stage 10 is the backfilling. And then we followed it with another stage where retaining wall R4 was constructed at the very bottom. Now, when you do such analysis, there are several things which comes together. So we have water table and we have seepage lines. So first you have to ensure that you need to figure out what is the phreatic surface, what is the water table, whether it is fluctuating or not. So in GeoStudio, we have a module called CW, which helps us in finding out a steady state seepage line or a transient state seepage line. It is a finite element based solution procedure where you can figure out the seepage, phreatic lines, seepage lines, and the pore water pressure distribution either in steady state or in transient state. So steady state is the condition which I was talking right now, where we maintain a specific water table. And if there is rainfall, there will be fluctuations in the water table, and that's where the transient seepage analysis needs to be done. Along with that, so after we come to understand about the pore pressures and the condition of the water level, so then different constructions were done over the site. So we had the retaining wall, the buildings. So they gave some amount of load, and under that load deformation will take place. And sigma W is a module in GeoStudio which helps us to get the idea about the load deformation response. Again, it is a finite element based system. So from this load deformation response, you can figure out how much of deformation is taking place, how much of stress is getting generated over the entire section. However, one thing we should remember, that since water is already present, the load deformation response will be affected by the pore water pressure already generated. So in the GeoStudio, we have a concept of parent-child. So where the left portions, each of the preceding left-hand module serves as the parent, and each of the succeeding right-hand module serves as the child. So CW we start with, we get the pore pressures, pass on this to the child, sigma W. There we do a load deformation analysis with the pore pressures included and try to figure out what is the load and deformation or the stresses generated in the medium. And based on the stresses, we pass the information to slope W so that we can carry out a stability analysis, figure out what is the factor of safety, whether the slope is stable or unstable, but by considering the stresses generated from the sigma W. In general, slope W is used without, can be used without any stress generated from sigma W. Just on the geometry, you will try to figure out what is the stability. But in such forensic analysis, it is very important to understand what is the pore pressure and stresses generated and how they affect the slope stability or instability generated. So these should be applied in sequence when you do such failure analysis. C, that is the pore water pressure analysis, sigma, that is the load deformation analysis, and finally slope W, the stability analysis. So we started looking into these analyses in stages, and finally we are basically interested to first of all look into whether the slope is stable or not. So in the slope W, in slope stability analysis, we use Morgenstern Price method because water was involved in this. and entry-exit method for slip surface definition was given. So we considered from some location the slip surface starts, and at some location it ends. So there is one specific method in GeoStudio Slope W, which you can figure it out from the software manuals. So at stage 1, that is when the in situ thing was there, so we could figure out the factor of safety is 1.4, quite high. So the slope initially was stable. So we did not have any instability in its virgin condition, and that's what we have seen in the field. Then in stage 2, when the excavation was done for the building, still the slope is stable, 1.373. So that means just the excavation did not start anything. However, when the building load started to get imposed, we could see that the failure factor of safety started coming below 1. Now in the field, it might, so any factor of safety below 1 means a complete failure. But in the field, what may happen is that the failure might have taken partially, gradually things have started. So over the long run, probably it would have failed completely. But due to the creep movement, the slow pace movement, the failure could not completely take place in the field. It went on for quite some time. However, the building load showing this factor of safety being 0.821, that means this building load imposition started to trigger our failure in this case. And then as we moved forward in stage 4, the building load was completely used and the backfill was done. Retaining wall was constructed, its backfill was completed, but you can see the factor of safety is always below 1. That means even this particular retaining wall, which was supposed to actually prevent further movement and make the slope move towards stability, is not helping. It might have slightly increased the stability, but it is quite less than 1. So if you see, this retaining wall is actually floating on the active soil surface, which is bound to move. That means this retaining wall is not really helping, but rather adding more weight on the moving soil mass, which would trigger more failure. Then the retaining wall 2 was constructed. But you see at stage 8, after the completion of retaining wall 2, now the slip surface passes below the retaining wall. So that means the retaining wall 2 is also not helping. The workers' colony is not getting sufficient protection from retaining wall 2. So retaining wall 1, 2, everything is moving with the active soil mass. And then retaining wall 3 was constructed in between that. It did not help again. It is simply floating on the active soil mass. So that means overall, all these slip surfaces, what we are seeing, are passing much below the retaining walls. And basically the retaining walls, which were supposed to prevent or protect, is basically on the other way, adding more weight and leading to more system destabilization. Interestingly, when we analyzed the retaining wall 4, which is at the very bottom, you can see that the stability have increased significantly, which gives a apparent indication that retaining wall 4 would have stopped the further movement, but it really did not happen in the field. Now, why such condition happened? You can see that the slip surface which have been generated is now basically trying to penetrate the rock layer, which is impenetrable. And because it is not able to penetrate, more resistance is generated here. And that's why probably the factor of safety increased. But in the field, what we have seen from one of our earlier figures as well, that the soil actually overtopped retaining wall 4. So that means retaining wall 4, although it could have stopped, however, the soil with the muddy water, the seepage water, overtopped retaining wall 4, and retaining wall 4 did not serve any purpose. And since this is not getting reflected in this particular analysis in the preliminary level, so that's why we need further investigation. So before moving on to further next step investigation, what we did, apart from slope stability, we looked into the stability analysis pictures. Because if you remember, we had 3 different soil stratigraphy model: PM, first borehole, SM, second borehole, and TM, the third borehole. And each of them were analyzed for dry as well as 3 different water table conditions. Now, if we look into PM and SM, now these soil stratigraphies which we adapted based on these 2 boreholes, borehole 1 and borehole 2, they really did not serving any purpose or readily not giving us any solution. Why? In the state of water table, wherever it is located, whether at the surface, whether at certain depth of 4 meters or whether at a depth of 8 meters, you can see at all the cases for PM and SM, the factor of safety is below 1. That means wherever the water table is located, doesn't matter. If this was the soil stratigraphy adapted, it was bound to fail. But not only that, even in stage 1, it is failing. So that means in situ condition also it would have failed. That means this states that if the soil stratigraphy followed borehole 1 or borehole 2, in the in situ condition only the slope stability or slope instability would have taken place, which did not take place at the site. Looking into the tertiary model, what we could see that at stages 1 and 2, that means at the in situ and stage 2 where the excavation for the building was done, the stability was still there. So this gives us a more confident idea that probably the borehole 3 from which we created the tertiary model would have given us a better picture. So tertiary model indicates the imposition of building load stage 3, which basically have triggered the instability in the system and over which further constructions have triggered more instability. Now, in this particular case, what we can notice that in the dry condition, there was stability also till stage 2, if it was absolutely dry, hypothetically. Yet stage 3 in the dry condition would also have resulted failure. But in the dry condition, the retaining walls which were constructed would have again regenerated the stability scenario. But since water was present, the entire hill slope was in the unstable or marginally stable condition. So in this way, tertiary model 3 with the stratigraphy from borehole 3 gave us a more confident idea. Still, water table was an issue. So we tried to identify the location of the water table, now considering only the tertiary model, because its stratigraphy is seeming to be responding to better behavior as we have observed in the field. Then we tried to identify the water table location, whether it is at W1, W2, or W3, which one is more reasonable. Now see, all these informations were not there from the beginning. So that's where forensic understanding engineering judgment comes into picture, where you figure out the most reasonable thing. In dry condition, we could see, as I was mentioning in the earlier slide, that even in dry condition, there would have been marginal instability in stage 3 and stage 4, but the retaining wall constructions would have revived the stability. Now, when we assume the water table at any depth, 1, 2, or 3, we could see that from stage 3, the imposition of the building load showed similar instability, whether it is at shallow surface, whether it is at a moderately deeper surface, or whether water table is located at large depth. So under these scenarios, when we considered, if you remember this figure, we considered steady state water seepage lines. So that means these are the phreatic surfaces of W1, W2, and W3. Over that, the water will not recede. Now, under such scenarios, there will be no seepage reflected through the sloping face. But if you remember in the field, we obtained seepage water from the sloping face just behind the workers' colony where the slide had taken place. So in this particular condition, we could figure out that water table is definitely playing a role, but probably the steady state water table lines are not proper. So possible location of water table at this particular stage of forensic analysis still remains unresolved. Then we tried to see how the load deformation scenario is from the sigma W analysis. So for each of the analysis for the tertiary model and a dry condition with water table at shallow depth 1 meter from surface, water table at W2 4 meter from surface, and water table at W3 8 meter from surface, we tried to figure out based on our analysis how much of deformation took place on the slope face, lateral deformation. Before going to that, we should remember that this is our preliminary model, and the 24 colonies located at 170 meter from the workshop. So this is a total model width of 240 meter. From the workshop, it is at 170 meter. From the workshop building, the 24 colonies located in the field where the damage has been extensive. So when we looked into that, when we plotted the lateral displacement over the entire face of the slope. So horizontal extent of the slope is in x-axis, and we plot the resultant displacement in the y-axis. Under that condition, we could see that at these locations, so this is 170 meter from the left end, from the store building or the workshop building, we could see that if the soil was in a dry state, there would have been no displacement at workers' colony location. If it is in having a water table at shallow depth, W1, some deformation in the workers' colony location is noticed, 1 to 2 meter. Whereas if the water table is at larger depths, W2 and W3, again, further no deformation is noticed. So that means this gave us an idea that with the tertiary model, the model using the stratigraphy of borehole 3, and with a shallow water surface, shallow depth water table at W1, 1 meter from the ground surface, we could still get a reasonable idea that there is a deformation near the workers' colony. So based on all these preliminary analysis, we could figure out, okay, let us move ahead with a stratigraphy using the TM model and water table at W1 and look further. But still, even if W1 seems to be the most probable, as mentioned, these are constant or steady state phreatic line. So they will not show seepage at this hill slope surface. So what are we missing? We are missing the rainfall. If you remember that in this particular case, rainfall had occurred as mentioned by the client, as I was mentioning earlier. And when we visited the site, we could see water seeping out from the slope face behind the 24 colony. Now, that's where the question looms, that if we are not considering the rainfall, then we will not see the rise of the water table, and that's what we need to inspect. So again, in the CW analysis, we considered the rainfall and rainwater infiltration from the meteorological and climatic data of that area, how much of rainfall took place in that particular year after which the event took place. We considered a prevalent infiltration, and we modeled that infiltration as a constant water head over the entire slope, because over the entire slope, the rainfall had occurred. And that led to percolation of the rainwater, and that led to the rise of the water table. So the water table earlier, which was going below the surface and meeting the rightmost point of the slope, now it has risen. So those inferences could be figured out, that infiltration has led to the rise of the water table. And as the water table has risen, you can see this blue line, that is the phreatic line. Now it is intersecting with the slope, which is near the 24 colony. And that gives us a good idea that whatever seepages we were seeing in the field probably is now coming from the rise of the water table due to the rainfall. So we moved one step ahead. Then we tried to see that rainfall has taken place over some hours, and a constant rainfall was introduced in the model. And we tried to figure out from the water flux variation along the lateral extent that at what time the water flux reached zero. So whatever the topmost plot you are seeing at 180 seconds, just after 3 minutes of rainfall. And then we started looking into long duration of rainfall. So 1 hour, 30 minutes, 1 hour, 30 minutes, 3 hours, 6 hours, 12 hours, and for full day, because more or less 8 to 9 hours of rainfall had been there. And when the water flux is measured, so this is the total flux which you are measuring, when this water flux is the additional water flux, when it comes down to zero, that means the water is seeping out from the surface. So this water flux, when the achievement of a zero or negative flux at the slope face is recorded, that's when the water table intersects. And what we could figure out, so this is the location where the colony is placed around 160 to 170 meter. And we could figure out that the lines representing 3 to 6 hours of rain, that those lines are basically meeting the zero water flux level. That means after approximately 3 to 6 hours of rain, the model is indicating that the water table has risen and the seepage water started to come out from the surface. And a similar coincidence and a similar observation was made in the field, that after 3 to 4 hours of rainfall, the initial movement was noted in the field. The initial seepage, the seeping water was recorded in the field, as well as the movement was noted in the field. And that's where we that's what we see from our field observation. So these are the locations where the water has come out from the surface. And you can see that R4 is quite below. And now as the water came out from the surface, so that wetted this entire area, and the mud mud or the slurry type of material got generated, and it overtopped the retaining wall. So that gave us a confidence that the rainfall which we are modeling is good enough to talk about the water which is seeping out of the surface behind the colony area. But still we were unhappy. Unhappy in the sense that when we looked into the displacement all along the slope, we could figure out that there was very less displacement behind the 24 colony. While when we went to the field, the displacement behind the 24 colony is catastrophic. So it is a complete landslide which has taken place, which was not getting reflected from our model. So we could figure out that there was hardly 1 to 2 meters of displacement behind the 24 colony, whereas beyond the building, the storehouse, the displacement, the maximum displacement contour came out to be 10 meters, but which was not really getting reflected in the field. The displacement was less here, there were displacement, but on the steeper face, the displacement was higher. So that means something was not correct. So something was not matching with the field. The displacement behind the colony was like a carnage, where our model, preliminary model, is not showing that. Preliminary model is showing that beyond the storehouse, the displacement is maximum, which was not recorded in the field. So what did we miss? One very important thing we missed definitely is the borehole. There were no boreholes on the slope face or on the landslide site. So whatever we used earlier was from the crest, from nearby locations in the plant area. Now they need click termites, so they might not be working to give us a proper indication of the displacement. So since we were taking a different borehole, not really from the failure site, it might have happened that the stratigraphy is not getting followed, or even the soil parameters which we were taking, so may not be well reflected. So then what is the prescription? Then we suggested the client to do some more boreholes on the landslide site itself. Now, when we do suggest boreholes on the landslide site, one thing we have to remember that the site needs to be accessible, and in this case it was. So many boreholes over the landslide site were prescribed, some up to the bedrock level, some even deeper, and based on that, we could figure out some new inferences. When we looked into all these boreholes over the landslide site, our vision about the stratigraphy completely changed. So now very interesting things could be noticed when we placed the boreholes one after the other, and we could figure out the stratigraphy along the slope. Now, one very important thing which we noticed is the presence of a thick cover of loosely deposited fill soil for around 1 to 2 meters. Now, these loose deposits actually came from the construction of workshop, store, or any other soil excavation which was done, and they were simply dumped on the slope. And at the very beginning, the client thought it was best not to reveal that such things happened. So this was for the first time from this borehole, we could make an idea that the upper soil is not really a virgin soil, but a fill soil, which always remains bound to move. The next important feature which we found out is a shell pocket. Now, shell are very interesting materials. During its dry condition, it will be enormously stiff. As soon as water starts percolating, it will be very slippery, and it will give the shear surface, which can trigger a superficial failure. Then we have a weathered rock stone, another interesting material. Now, since they are weathered, they will allow very easy percolation of water through them. So water can go deep and it can saturate the entire surface. So gradient-based migration of water beneath the slope surface can take place. And finally, we have a thick bed of shell. So in any dry condition, it will be like a bedrock, very stiff, but when again wet, it will offer a sliding surface. So now what we had basically is a fill layer over which everything stood. The building, the retaining wall, the workers' colony, everything is on the fill layer. None of their foundations are also going even up to the shell or the weathered rock stone. So we thought, let us change our methodology. So a new understanding of the failure site came into picture, and we had a strong intuition that whatever failure we are seeing is not really a deep-seated failure, but rather a very shallow surface failure on the fill itself. So since all the buildings and infrastructures are on the fill, so they are obviously bound to move if the fill starts to move in any case, because none of their foundations are penetrating the fill layer and going beneath. So that's when we started looking into a new numerical model. Now you can see this is quite different from the one which we gathered earlier. So we have a fill cover, we have a top shell pocket, then we have weathered rock, and then we have the bottom shell. But then since our intuition told us or gave us a hint that it is only the fill layer which is moving, so what we did is that we only modeled the fill layer as a deformable layer and all the other three layers with their properties as impenetrable layers. So we do not want the slip surface to basically penetrate in that, and we want only to see whether the fill layer is the culprit. And then accordingly, from the new boreholes, we could figure out the model parameters. You can see the fill layer is taken as elastic plastic. So a load deformation movement can take place, whereas the other ones are linear elastic. So it is a very stiff type of material, what we assumed for this case. You can see the difference in stiffness as well. And as earlier, we constructed all the building loads and retaining wall loads in stages, sequential analysis, whatever we did earlier. So we had the building load, then we gave R1, then we gave R2, then we gave R3, and finally R4. And we did all the stages of analysis, what we discussed earlier. And now, interestingly, the things started to make more sense. You can see that in the earlier case, when we were talking about the dry condition, there we saw that under the dry condition also, when the building load was imposed, the thing started to move. So there was instability generated. But in practice, it did not happen. The instability actually occurred after the things got saturated, got wetted by the rain. Now with this new soil profile, you see that under the dry condition, hypothetical dry condition, if whatever loads we place, it is always stable. So at least that matches with the field observation. And then when we look into the saturated condition, when the rainfall has wetted the system, so in the in situ condition, it was marginally stable. You can see it is 1.014. So just stable. And then with the, even with the colony load, things have started to destabilize. So colony was a lightweight structure, but since it was created on the field, on the steep slope, that also triggered a movement. And slowly you can see with the more and more construction, the movements were, or the stability was jeopardized more and more. We did not stop there. We started looking into the deformation contours and try to assess what happened. So when we added the colony load, you can see that a good amount of deformation, not much, maybe around 2-3 meters, brief deformation had taken place, which might have gone unnoticed. But now with the building load, when we gave the building load, you can see that the deformation contours are getting well spread, more deformation near the building, comparatively much lesser deformation at the far end. Now this building load started deformation over this particular slope. And then people thought that the slope is moving, let us give a big retaining wall here. So the retaining wall was given, but the system of soil mass was already active. The retaining wall added some more load, and you can see that the deformation contours have now started spreading towards the downhill side. People thought, oh, there is a movement in the downhill side as well, put some retaining wall in front of the colony. So that's where the R3 was given, R2 was given. But now because of this load imposition, these two deformation zones started overlapping each other. And when deformation zone starts overlapping each other, that is a catastrophe where more deformation is bound to occur. So with the giving of R2 also, things did not stop. In the field, people noticed still things are moving. The road, the access road was moving. They gave another load in terms of retaining wall R3 in the place in front of the access road. And now you can see the catastrophic case that all the building loads and retaining wall loads getting mobilized. Now the two deformation zones have matched each other, and a significant amount of deformation here with superficial deformation of around even 18 to 20 meters have taken place. And that led to complete mass movement and complete failure of this system, which we have noticed in the field. Another interesting thing which came into picture, the retaining wall R4, which was at the very bottom. Now you can see all these arrows are overtopping R4, which we noticed in the field as well, that R4 really did not help, which was apparently helping in our previous model. In this model, which is more realistic to the field scenario, it is not really helping. The soil mass is moving over R4 and it is not really supporting any prevention. So over this R4, you can see a lot of movement is there. So R4, that is the bottommost barrier, got overtopped by the excessively displacing soil. So that's where our forensic analysis ended. We could figure out stage by stage how the movement took place, how the deformation took place, how the triggering and the overtopping took place. So we could identify the background reasons of the cause, triggers, and subsequent failure, and especially based on the new set of boreholes which we had conducted over the landslide site itself. And we got a good match, not only with the displacement monitoring stations, not only with the displacement values, but also with our observational values from where the seeping water is coming out. So all those features we could trace back. And then the client also requested us to give us some stabilization scheme. Again, we spent a good deal of time that which stabilization scheme we should be choosing for this. We modeled with cutoff sheet pile wall, whether 2 layers or whether 3 layers, and we tried to see whether they could arrest any further movement in the future. So these sheet pile walls are to be pushed, and one thing to be remembered, they have to clear up the filling space, filling the fill layer, and they have to move into the weathered rock or the bottommost shell. So they have to be pushed into the weathered rock layer. So we figured out some strategic locations and the height of the sheet pile walls. Several trials were again done for that. And then when we look into the factor of safety values before the stabilization, and you can see that after in situ stage, there were the marginally stabilized or fully or complete failure from the lower factor of safeties. Now, when we have adapted the 2 layer or the 3 layer of cutoff wall, we could see that they are quite stable. Whether it is now 2 layer or 3 layer to be adapted, that depends upon the economy of the project, utility of that site in future, and all the other things. So at least one thing we could figure out, that this cutoff sheet pile wall could provide us a successful stabilization scheme, which we could notice from this stability analysis. Not only that, with that stabilization scheme, we could see that we could arrest the deformation in a significant manner, even at the steepest point of the slope. So not much deformation has taken place after this is analyzed with the sheet pile walls. So as final remark, so as I was mentioning, the domain of forensic geotechnical engineering, it is basically to understand the failure after the incident has occurred, and whatever steps I had mentioned in that framework, each of the steps you need to go through in any such forensic analysis. Now, always remember, geotechnical problems are unique. So for each of the steps, you might have to use your engineering judgment, your engineering expertise, which comes over the time. So steps or the framework remains the same, but the nitty-gritties of each of the steps starts changing depending upon the problem, the way in which you are addressing, and the way in which you are getting the data or seeing observations in the field. So lastly, I should acknowledge my colleagues. We all 4 were there for this project, myself, Dr. Bharat, Dr. Murli, and Dr. Anil. And in this location was actually very beautiful, just on the left-hand side where we had all the trouble. On the right-hand side of the road, we had the beautiful Umrangshu Falls, which serves a great deal of water for the hydroelectric power plant of that area. And finally, I would like to thank my students, Priyanka and Rupleka. So they were the driving force. They did all these analysis, probably this total number of analysis which was done for this entire project was nearly 2,500 or so. This project extended for 2 years span, and we could learn a lot. And definitely thanks to Calcom Cement who approached us, we could help them. But more than that, we learned lots and lots of knowledge we could gather from the project. Some publications we had, if you want to see, you can visit my website or the ResearchGate profile. So that will be all from my side. I thank the organizers for letting me in this particular FDP program. I could share our experience, share our knowledge, what we gained from this project. And definitely thanks to the audience for having a very patient time hearing about our project and whatever I had to share. So thank you all. So thank you, Madhulisha. Then over to you.
Thank you so much, sir. It's really enlightening lecture. The session was also very, very interesting and valuable and very informative. So now I think any queries, participants, do you have any queries? You are requested
Actually,
to unmute yourself.
I don't have query as such, but then just an inquiry that it's all the underlying principle is limiting equilibrium analysis. We also have, like analysis based on probability based analysis. So in the slope stability, what is the field situation that limiting analysis is equilibrium analysis is giving satisfactory results? I mean, failure is still happening in the site. So is it that we should not move with probability analysis also? Because
so I understood your question. I would address it in this manner. Two things are getting mixed here. So as you were mentioning that this is limit equilibrium, this is not really limit equilibrium. This is already combined with the finite element analysis as well, as I was mentioning. But yes, your anticipation is quite right that the instabilities are still happening at site. And that's where probably probabilistic analysis.
Because just shifting entirely, you just shifting, entirely given boreholes to like additional boreholes, so much money is required. So you see that this over consolidated kind of condition for which we take residual strength parameters. So it was ensured
I will answer your question.
Soil is not over consolidated. That analysis was done, that it is an NC soil or OC soil.
Let me finish. I was still answering your earlier question itself. Okay. So when we do probabilistic analysis, we have a lot of resources what we need to still have. So I understand that we could have done, but one thing also you need to understand that these sort of probabilistic analysis will still give you that uncertainty phase still involved with the system. So in this type of consultancy projects, in this type of consultancy or practical site investigation projects, especially the forensic ones, even if you do probabilistic one, probably you will still see that there was failure. So in this particular type of analysis, although probabilistic analysis might have given us a little bit different insight, but whether better or worse, that we really not able to tell. But from academic front, definitely.
Like for your PhD students can still investigate, right?
Yes.
Because yes. At your location site, that's what this interaction is all about, isn't it?
Correct. So
develop an efficient kind of system. So that is. So yeah, that's the objective. So if they can take a probability-based approach in your location, and then what results they're obtaining, and then how it is matching with the limiting equilibrium approach. And also, like whether the soil, if it is over-consolidated, we should take residual strength parameters to do the analysis. So all those things.
Yes, I was still answering your question. Yeah. So to mention, see, as I was mentioning, from the academic front, definitely we can do a lot of activities, and definitely my PhD students recently, Ruby has completed completely on the probabilistic front, where we look into the probabilistic limit equilibrium part as well, and probabilistic finite element part as well. And it is not really about whether it matches or not, whether it gives you the perception or not. That is what is more important. See, something will match and something will not. Whatever uncertainty lies with the soil parameters, that will ever be. And however probabilistic study you carry out, always there will be some match and mismatch. So it is not about matching or mismatching. It is about the perception of the geotechnical problem, whether it is well reflected or not. Yes, in any site, probabilistic approach is definitely needed. In our system of geotechnical engineering, it is still evolving. It is in a very infancy stage. We are still working much on the probabilistic front. A lot of things are coming up. Academic front, it is going on very good. But when you go to the application front, still we are a lot behind to apply it in the particularly field practice domain, especially since our codes are still age old. One thing we should always remember, that whatever advances we are making in the academic front, always a barrier comes to us, the codal provisions. Codal provisions yet do not include in that with the probabilistic one. The people are trying. And once it comes, definitely, I'm sure the probabilistic analysis will get more into the action. If you see the codes outside, BAS, FHWA, and NHCRP, all these codes have really moved into the probabilistic front. And now for them, we really do not work with the deterministic analysis. And the other thing which you mentioned, yes, if it is over consolidated or normally consolidated. Now, since I was mentioning that it is a fill material, right? So this was all normally consolidated material, not over consolidated. And yes, if it is over consolidated, we could have taken the residual strains, or residual strengths, basically. So those were done. So if you again revisit the video recording which was given, so in those you can see the short-term parameters as well as the long-term parameters were used. So both the short-term and long-term analysis was done. And that's where I was mentioning that in one particular place that just by imposing the building load, it is showing failure. But that is a long-term parameter failure. In the short term, it might not have failed. It might have just initiated a creep type of failure movement. And that's what was reflected with lesser amount of deformation near the building. So all those were done in this case also, but not probabilistic case.
Yeah, madam, very nicely organized. But then, like we are not supposed to stuck at one point. Like everybody is doing their things. What I see, each interaction, some progress in one direction. So nobody is supposed to stuck at one point. We have to move ahead. Okay. Thank you, madam. Thank you. That will be from us.
I really did not get your point. Means stuck at one point, move ahead.
Yeah, because each, you are knowledgeable, see that why residual strength analysis has not been done, and what is the benefit of incorporating the probability-based analysis? Because at times we have limitation in the limiting equilibrium analysis, isn't it? So that's why probability-based analysis has been introduced. But then we haven't investigated it. It is in the infancy state because the failure in the real situation is like this. But then I would always suggest that probability-based analysis, has to be, carried out, for better understanding.
Correct.
Why we have, even if it is 5% of the failure, why is it? I mean, can we minimize it? Can we make it more efficient?
That's correct. But
if we are able to make it efficient, we all see the benefit of it, isn't it?
That's absolutely correct. But you will still face the resistance when you take up these field works, in the sense that when you show them the probabilistic analysis, see, our overall expertise in the probabilistic analysis have not yet gone to that level. So that resistance is still there. And all the government agencies, all the government or even the private agencies strictly follow the code. So first, we definitely need to strengthen our codal provisions, or rather update our codal provisions. And definitely, I think this should come into more and more practice. I agree with you.
Yeah, that will be our madam.
Okay, any more questions from the participants? So now
Okay,
I think
okay.
Is there anything? No, sir.
No.
Okay, sir. So now I think the queries of all the participants have been addressed, and it was very beautifully explained. So there is no doubt many of the participants, that's why they're not asking questions. Maybe they're clear. Sir, it is an honor for me to invite you to participate in this FDP as an expert speaker.
Thank you.
And thank you so much for accepting the invitation. Thank you a lot, sir.
Thank you. Thanks to all the participants for listening. Every presentation has a takeaway, even if it is 1%, and that changes many things in future. So all the best to everybody.
Thank you, sir. Thank you so much.
Okay, thank you.
So participants, we will meet again on tomorrow for our next session. So all the participants are requested to kindly assemble on the same virtual platform for the session. So in order to avoid any last time technical issue, you are requested to join 10 minutes prior to the session time. And also all of you know, all of you that are aware of that, about the ATAL academy guidelines, that you will receive a e-certificate in your account only if you will attend 80% of the session and score 60% of the mark in the test, because as for the ATAL guideline, this one. So I'm requesting you, to all of you, that please do the needful. And thank you all for your patience of listening. Thank you so much. So we can stop here.